My name is IZZATI and I'll be presenting for literature review part. For natural gas properties, it consists of a hydrocarbon mixture which is methane, ethane, propane, butane, and the least is pentane. Methane is the most abundant, typically up to 85%, and then this gas will be compressed into liquid for transportation reason. The main use of natural gas is for electrical power generation, and it is favorable compared to fossil fuel due to low carbon dioxide emission during their burning. And because of this, the economics of natural gas shows increment from year to year, as you can see in this graph. And from this trend, it is expected that the natural gas consumption is going to increase in the future too. And then the properties of the compounds. Okay, take a look from methane, ethane, propane, carbon dioxide, and hydrogen sulfide. They share one common trait, which is colorless. And this explains why the natural gas is in the colorless form. And because of these compounds present, the natural gas is actually flammable if the condition is favorable. Okay, for selecting the best site location, we are going to compare among three locations, which are South China Sea, Malaysia, Java Sea, Indonesia, and Gulf of Mexico in Mexico. And there are 10 criteria need to be fulfilled. Okay, and these criteria are going to be graded accordingly. 5 is the highest, 0 is the lowest. Okay, and it is shown that South China Sea, Malaysia has the highest mark, which is 43. And this is due to the geography where Indian and Pacific Ocean is connected and many tradings are happening here for many countries. And then for the markets, the good trade is 5 trillion per year, which consists 50% of LNG at least and 25% of crude oil. And then for the corporate income tax, Malaysia has the lowest for the income tax for the South China Sea. And then the natural disaster, it is considered to be the safest compared to other locations.
Next, we'll discuss about the market demand. The energy challenges faced by the world are the growing population, to provide a higher standard of living, to provide an alternative to cleaner solution, and to mitigate climate change. In the current market, LNG demand is highest in Asia, followed by Europe, Middle East, and South America. The main consumer in the Asian region are Japan, South Korea, and China. LNG production is recorded to be 359 million tons per year, and its demand is expected to hike 3.6% every year. However, the demand is higher than the supply, thus there is an emerging LNG supply-demand gap as shown in the figure. Factors that contribute to increase in demand are, firstly, the government policies to encourage usage of cleaner energy. Greenhouse gas emit from natural gas is 45% to 55% less than if coal were combusted. Example of government policies are South Korean taxes to favor gas over coal. Secondly, LNG provides required flexibility for power generation and meets seasonal needs. And lastly, new countries choosing LNG to replace oil-fired power generation. The main concern in safety and environmental issues are compliance with the OSHA standard, precaution against fire and explosion, preventive method to reduce risk of leakage to the environment, and lastly, employee need to be protected against noise and hazard during operation.
Process screening and mass balance under conceptual design. For process screening, let's take a look at our process overview first. Here we have our major processing units in order. First, the natural gas stream will undergo mercury removal via adsorption using Hg sieve, which is a molecular sieve. Secondly, the mercury-free natural gas stream is fed to an acid gas removal unit where CO2 and H2S are removed by scrubbing the gas stream with diethanol amine, also known as DEA. Next, the natural gas is dehydrated via absorption using triethylene glycol, also known as TEG. The contaminant-free and dry natural gas is then cryogenically fractionated into a high-purity natural gas stream and its respective natural gas liquid streams. Lastly, the streams which are in gaseous form are liquefied to facilitate transport and storage. Now I'm going to explain the significance of each process unit and the available options we considered. Let's start with the mercury removal unit, also known as the MRU. Mercury is most frequently found in its elemental state in natural gas reservoirs. This means that it is pure mercury, not chemically bonded to any other elements. The largest risk mercury poses to operations is its ability to form amalgams with exposed metal surfaces, such as those found in pipelines and equipment internals. Mercury has in the past caused significant damage as it reacts with and corrodes the aluminium heat exchangers used in LNG processing. Corrosion causes reduced equipment and piping structural integrity, leading to high repair costs. If left unchecked, these may cause leaking, pitting, and eventually catastrophic failures in equipment. Due to the danger mercury poses, frequent maintenance and preventative maintenance checks must be performed to mitigate risks. Therefore, now that we understand the hazards of mercury, its removal is considered an utmost priority, and this process is put first among all the other processes to mitigate the risk of equipment failure downstream. The removal of mercury can be executed via adsorption using either UOP-HG sieve molecular sieve, sulfur impregnated carbon, or metal sulfide on carbon or alumina. We have chosen A in our process because mercury has a high affinity for precious metals, gold, and silver. Since the HG sieve molecular sieve is a molecular sieve which has been coated in silver, its removal efficiency is much higher than the other options. Furthermore, the high removal efficiency reduces downtime caused by mercury-induced corrosion while ensuring safer operations. The UOP-HG sieve molecular sieve is regenerated using heat, saving costs as it can be reused. The mercury is then removed from the natural gas stream via the regeneration gas stream. From natural gas. Acid gas refers to carbon dioxide and hydrogen sulfide in this case, which are also known as CO2 and H2S. It is important to remove CO2, a non-flammable gas, from the natural gas stream as it directly impacts the flammability of our final product, which is LNG. In terms of process, the cryogenic temperature in downstream processes can cause dry ice formation or solid CO2 in the pipelines and equipment. This can reduce the flow rate in pipelines and even damage equipment internals. As for H2S, it reacts with water to form a weak acid which can corrode piping and equipment internals. As was the case for mercury, corrosion could lead to leaking and equipment failure in the long run. Therefore, incurring additional maintenance and repair costs. Additionally, H2S is poisonous to humans, especially when inhaled. As such, these acid gases are to be removed via scrubbing. The solvent options include diethanol amine solution (DEA), monoethanol amine solution (MEA), and methyl diethanol amine solution (MDEA). DEA solution is selected as the solvent of choice since it has superior CO2 removal efficiency compared to MEA and MDEA. Furthermore, this solvent can be regenerated via heating in order to be reused in process. The acid gases are then re-injected into the reservoir to maintain pressure in the well. From the natural gas stream. It is necessary to remove water as much as possible to prevent the formation of hydrates in pipelines at low temperatures. A hydrate of methane, for example, is a solid structure formed when large quantities of methane are trapped in the crystalline ice structure. Having hydrates formed in pipelines will restrict the flow of natural gas and may cause choking and pressure differentials in the pipeline. Moreover, a high water content in the natural gas stream may allow for the formation of liquid water, which could over time cause corrosion. Therefore, dehydration of natural gas is necessary. Our options are to remove water either using absorption using TEG or adsorption using either solid silica or alumina adsorbents or molecular sieve. Absorption using TEG is chosen because in terms of performance, it has comparable water removal efficiency as adsorption. Furthermore, it requires lower capital cost investments because as opposed to adsorption using the molecular sieve, it does not require redundant units for regeneration purposes. What's more, absorption using TEG allows for top-up of the solvent without downtimes and without having to stop operations. Natural gas is performed to produce high-purity LNG and separate the natural gas liquids. Through this process, our target is to produce liquid natural gas with at least 90% methane, in addition to high-purity natural gas liquid streams, which include ethane and propane. The two options considered were cryogenic fractionation based on component boiling point and volatility, and extraction of natural gas liquids via lean oil absorption. The first option, fractionation, was selected. This is because fractionation has higher separation efficiencies of the components without having to have a greater number of equipment units. Unlike absorption, fractionation does not require a regeneration column since no solvents are utilized in the process. For fractionation, two columns are required. The first is a demethanizer, where the mainly methane stream is removed as the light component in gas form. This will form the LNG product. The bottom stream of the demethanizer, which consists mainly of ethane and propane, is fed to the second distillation column called the deethanizer, where the ethane is separated as a light key and propane as the heavy key. Based on simulations using Aspen HYSYS, the LNG purity achieved was able to reach 97%, with at least 99% purity in both the natural gas liquid streams. Liquefaction takes place. The purpose of liquefaction is to ease storage and transportation, since natural gas in liquid form takes up only 1/600th the volume of gaseous natural gas. In the liquefaction process, refrigerants are used. The options presented are the use of either nitrogen or propane as the refrigerant. We chose nitrogen due to its being readily available from the atmosphere, as well as having high cooling efficiency. With that, I conclude the process screening and will pass the floor to my teammate Sashi.
Good day everyone, I'm Sashikumar Ravichandran from Group 19. Now I will be presenting preliminary mass balance for the process of this plant. First of all, dry natural gas feed composition are given. So using this data, dry natural gas feed mass flow have been calculated via reverse calculation by considering the criteria of obtaining 90% refinery of methane as the end product and the production of 100 million ton annually. So the mass flow that we obtain is 163,824.19 kg per hour. As the feed is saturated with water and the dry composition and mass flow are known, the water saturation process need to be done to identify the wet feed mass flow and composition, and it have been done using Aspen HYSYS tool known as stream saturator. The mass flow of water needed for saturation process is 1038.63 kg per hour. Moving on, mercury removal unit. As the feed contaminated with mercury content, it need to be removed, and it have been done using mercury removal unit by adsorption process using HG sieve adsorbent. Assuming 100% efficiency, the mercury content in the feed up to 50 ppb fully removed, and the product of the process will be out of mercury composition. Moving on, acid gas removal unit. Acid gas in the feed, carbon dioxide and hydrogen sulfide up to 25% and 500 ppm respectively also need to be removed, and it have been done using acid gas removal unit by absorption process using diethanol amine as solvent. As the end product of this process, only methane, ethane, propane and water are left in the feed, and water need to be removed next. Next, dehydration unit. Assuming 100% efficiency, same as other processes, the water content up to 2438.63 have been removed using absorption process with glycol as solvent. Now, only methane, ethane, and propane are left in the feed for fractionation and liquefaction process. That's all. Sujin will be presenting mass balance for liquefaction and fractionation process. Thank you.
Streams achievable through simulation are used as the basis of calculation. From an initial methane content of 92% in the dry gas stream, the purity can be increased to 97% in the LNG stream. The remainder of the components are fed to the deethanizer via the bottom EP stream. Again, assuming 100% efficiency for the deethanizer, the feed to the deethanizer unit has a flow rate of 6,179.6 kilograms per hour, with an initial weight composition of 90% ethane and the remainder being propane. The top ethane stream has 100% purity, likewise with the propane stream, according to the simulation values. As such, 5,578.45 kilograms per hour of ethane and 601.15 kilograms per hour of propane are recovered successfully using the deethanizer. For the liquefaction of LNG, the feed stream, which is a liquid gas mixture and 97% methane, is fed to the separator after stepping down pressures using a Joule-Thomson valve. The vapor phase or the vapor stream is pure methane, and the liquefied natural gas or liquid stream is 96.67% purity at a flow rate of approximately 105,000 tons per hour. With this, I end the mass balance section and pass the floor to my teammate KHAIRUL.
For economic evaluation, we are looking at the net profit. Net profit is a total revenue minus with total cost. So in this project, it is see that the net profit is 41 million ringgit. So the project is said to making a profit and a feasible project.
In this part, we will discuss about different areas in process flow diagram. The first section in the process unit is the mercury removal section. Here, gas flows downward to the absorption column and leave from the bottom side. Mercury is absorbed on the surface of silver impregnated sieve on the absorption bed. Regeneration process is done by heating a portion of gas from the bottom of adsorption tower before being recycled back to the front of bed. After that, the gas without mercury enter acid gas removal section. Here, CO2 and H2S in the natural gas are removed by contacting with DEA solution countercurrently. Rich DEA solution are regenerated in the stripping tower before being recycled to the absorption tower. After that, gas without CO2 and H2S enter the dehydration unit. Water in the natural gas is removed by contacting with TEG solution countercurrently. Rich TEG solution are regenerated in the stripping tower before being recycled to the absorption tower.
Okay, so for process flow diagram, as you can see here, there are two distillation columns named C501 and C503, and these two distillation columns are for fractionation process. Okay, so for the top product of C501 will enter this LNG heat exchanger E602 for refrigeration system, and then the liquefied natural gas will enter the flash drum to separate it from vapor. All right. So for fractionation, the separation of dry gas stream is actually based on boiling points and volatilities. And because of this, the most volatile component is going to be separated first. And the order is from methane, ethane to propane. Besides, this fractionation process consists of two processes, which are the methanizer, where the methane becomes the top product, and the ethanizer, the ethane becomes the top product. Okay. So for liquefaction, the LNG is from the distillate products from the methanizer column. Again, from here, it's going to enter LNG exchanger E602. And then since it is in vapor state, it needs to be liquefied first before being stored in storage tank. And then this can be done by using nitrogen as the refrigerant and follow the second law of thermodynamics, where the heat flows from high regen state to low regen state until it reaches an equilibrium state. And this liquefaction process, the refrigerant needs to achieve and maintain its temperature at negative 162 degrees Celsius. Okay. And then the flash drum is to separate the vapor where the LNG becomes the bottom product as in the form of liquid.
Now, I'm going to present another major part of process plant design, which is heat integration. What is heat integration? Heat integration is a method that used to increase the energy efficiency of the process plant. For example, in our case, liquefied natural gas plant, without changing any process or product by themselves. Not only that, heat integration helps to reduce the overall cost of the process plant by fully utilizing the available energy, whereby it eventually will minimize the energy requirement of the hot and cold utilities. The technique that have been used to carry out heat integration is pinch analysis. There are several reasons of choosing pinch analysis. First, it helps to determine the possible placement of heat exchangers and the utilities in the stream. Second, it helps to minimize the energy requirement by the utilities as well as maximize the energy recovery of the plant. To perform pinch analysis, King software have been used to obtain the results. This table here shows the stream data of the plant. There are a total of 9 streams, including 7 hot streams and 2 cold streams. This data shows the supply temperature, target temperature, heat capacity, and the enthalpy of the stream. For minimum temperature difference, delta T mean, the chosen temperature is 10 degrees Celsius, as according to the research, this value is more preferable for hydrocarbon refining industry. Next, how to perform pinch analysis. Two different methods, composite curve and problem table algorithm. Problem table algorithm is recommended as this method is much more easier and more precise to obtain the minimum utility requirement. Next is heat cascade. By doing heat cascade, we can obtain the minimum utility requirement. For hot utility, this plant will require 0 kilowatt, which means there is no need of hot utility in this plant. For cold utility, the amount needed is 226,527.85 kilowatt. The pinch temperature will be 418.9 degrees Celsius. The hot pinch temperature will be 423.9 degrees Celsius, and the cold pinch temperature will be 413.9 degrees Celsius. Next is Grand Composite Curve GCC. GCC provide hot and cold utility requirement in terms of enthalpy and temperature. In this plant, all the streams are fall under below pinch. And considering the both criteria, enthalpy and temperature, the best option that need to be placed for cold utility is cooling water. Next, heat exchanger network HAN. There are 7 new heat exchangers have been placed to exchange the heat between the streams, and there is a comparison before pinch analysis and after pinch analysis. Before pinch analysis, 9 utilities have been used, and after pinch analysis, only 3 utilities have been used, which are coolers. And if you see, splitting method have been used to obey the heat capacity rule below pinch, which are heat capacity of the hot streams should be higher than the cold stream. Finally, summary of heat integration. There is comparison between before heat integration and after heat integration. The overall heat duty saved after heat integration is 55,124.02 kilowatt, and the overall heat recovery is 19.6%. That's all. Thank you.
In this section, we will discuss about different control strategies for each process unit. Firstly, in the mercury removal unit, the main control in the molecular sieve operation is the switching valve operation. The duration of bed operation under different conditions should be optimized to ensure removal of mercury. The temperature profile in the molecular sieve beds must be monitored to ensure that the beds are fully generated before they are returned to the absorption cycle. The regeneration heater is controlled in the steam side to maintain the heater outlet at the optimum regeneration temperature. Secondly, in the acid gas removal unit, it is divided into adsorption column and stripping column. In the adsorption column, to maintain the amount of feed in the absorber, the flow rate of sour gas feed is controlled. Secondly, to maintain the liquid level in absorption column as well as flow rate of bottom product, the opening of valve in bottom product is manipulated. And lastly, to maintain the temperature of lean amine solution, the flow rate of cool side in heat exchanger is manipulated. Additionally, the control strategies in the acid gas removal unit are to maintain the amount of feed in the stripper by manipulating valve opening at the feed of the stripper. Secondly, to maintain the level of stripping column by controlling liquid level as well as the amount of regenerated DEA. This is done by manipulating valve opening at the stripping column bottom. Thirdly, to maintain the level of stripping column by controlling liquid level in reflux drum as well as the amount of reflux entering stripping towel. Thirdly, to maintain the temperature of stripping towel by controlling the temperature of reboiler as well as the amount of steam entering reboiler by manipulating valve opening at the reboiler steam. Besides, the control strategies in the dehydration unit is very similar with AGRU, as both process use absorption as well as stripping unit for regeneration process.
For fractionation process control, first we need to maintain the column pressure. This is because the column pressure affects the component volatility, and we're going to relate it with temperature because PV equals to RT. Let's say if the temperature of the column increases, the pressure controller will regulate the valve to let more cooling water enter and cool down the system. And then this condenser also needs to maintain its liquid level because it affects the heat exchange area. If the liquid level rises above the normal, the heat exchange area decreases and causes the pressure to increase. So the controller will regulate the valve to let out the excess liquid. Okay, and then to maintain the amount of the feed gas. Okay, this is because to avoid overflowing or underflowing of the gas. Okay. Besides, we also need to maintain the liquid level of the reboiler. This is because reboiler is used for heating. And let's say if there is nothing to heat, but if there's nothing to heat, but the system is still running, the reboiler will soon burn out. So that's why the pressure transmitter is used to detect the increment of the pressure drop and regulate it accordingly. Okay. After that, for LNG heat exchange, okay, the temperature transmitter here detects the natural gas temperature and regulate it accordingly here. Let's say if it is too hot, so the controller will open and let more nitrogen flow rate to enter to accommodate the heat exchange process. Okay, after natural gas is being liquefied, okay, the flow rate of the natural gas needs to be at optimal rate before entering the flash drum. So that's why it needs to be controlled here. Okay, and then since the flash drum is we are dealing with the vapor here, so it means that the pressure must be something very sensitive. So that's why we need to detect the pressure, and if it is deviated from the set point, we need to regulate it accordingly to avoid explosion. And the same thing with the flow rate to avoid flowing, underflowing, or overflowing. All of these systems use the feedback system. Thank you.
Okay, next we move on to hazard analysis. There is three knot selection. The first selection is the feed into the hydrator column. Then the second one is the feed into absorber column, and the third knot is the feed into the demethanizer. So we proceed with hazard analysis. For hazard analysis, the first parameter we are looking at is flow. The consequence of too high flow and too low flow is same for all the three nodes, which is too low flow will result to production loss, too high flow will result to pressure build up that will lead to explosion. The second parameter is temperature. We focus on the absorption first. For the absorption column, too high and too low temperature will result to inefficient absorption of the acid gas. So we move on to nodes number 2, which is dehydrator column. So dehydrator column, too high temperature and too low temperature will result to inefficient dehydration of water from the gas. So the third node, which is the feed into the demethanizer, too high or too low temperature of the feed will result to inefficient separation of the gas. So we move on to the last parameter, which is pressure. Too high pressure and too low pressure have the same consequences for all the three nodes, which is the low pressure will result to production loss, and too high pressure will result to pressure build up that will lead to explosion. So the prevention method for this overpressure problem is either can be passive or active. For active is control system, and for passive is pressure safety valve or pressure relief valve.